What would happen if the sun turned into a black hole? This question is so popular it was asked on the National High School exam in Brazil in 2022. The alternatives ranged from impacting the orbits of the planets, causing them to spiral towards the black hole, to beginning to precess more rapidly. The answer, however, was simply that the orbits would remain unchanged. This may sound strange, but since the only thing that affects the orbits is the mass of the bodies, if the sun were replaced by a black hole of the same mass, nothing would change for us here on Earth. Besides the eternal darkness and freezing cold, of course, there's that. But a question I bet you've never asked yourself is, what if there is a black hole at the center of the sun? And no, I'm not talking about a black hole suddenly appearing at the center of our star right now, or anything like that. I'm talking about, what if there's perhaps a black hole at the center of the sun that has always been there and we never had any idea? You, very wisely, would probably argue that the sun would have been swallowed a long time ago. But recently, this idea has started to be taken seriously, and we even have a name for stars that have an internal black hole. Hawking stars. Very recently, 2 articles were published asking precisely this question. What if there is a black hole at the center of the sun? The author's proposal was to investigate this question through simulations and theory. And what they discovered was a surprise. Not only would it be possible for a black hole to exist inside the sun, but it would also be extremely difficult for us to detect any difference if that were the case. The best part is that, according to the articles, it is very likely that there are stars with black holes at their center. And who knows, perhaps the sun itself could be just one of them. But hold on, let's take a step back. I know you are probably wondering if everything you learned about stars or black holes was a lie. And the answer is no, but there might actually be things about black holes that you still don't know. And that's why we're going to start by answering what a black hole is. But I promise that this time it will be in a way you've never seen before.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
What is a black hole? Black holes are regions of space-time with such extreme curvature that not even light can escape. And that's because the curvature of space-time is what we interpret as the gravitational field. We are stuck on the surface of the Earth because its mass distorts space-time. And this concept comes from Einstein's general relativity. According to the theory, matter and energy distort space-time, creating the effect of a gravitational field. To put it this way, it's even difficult to call black holes objects, since they are regions of the universe where everything that enters doesn't leave, not even light. The problem with this explanation and the name black hole is that it conveys the idea that they are holes in space-time that suck in everything they encounter. But the truth is completely different. Black holes are very picky eaters, and when I say that, I really mean it. The process of accretion, when a black hole swallows matter, is extremely complicated, and we have many unanswered questions. For a long time, one of these questions was, if an object around a black hole has angular momentum, then it will always remain at that radius and speed because angular momentum is conserved. But we know that black holes feed, so this means that objects are falling into them. In other words, these objects lost angular momentum. So how can objects lose angular momentum if it must be conserved? It was in the second half of the last century that astrophysicists realized angular momentum must be transported from the innermost part to the outermost part. And this causes a gas cloud to become a disk, where the inner part loses angular momentum and falls into the black hole, while the outer part moves away. And this disk is called an accretion disk. But what causes this transport of angular momentum? The answer only came in 1991. It was then the hypothesis emerged that magnetic fields cause friction and transport angular momentum. This solved one problem, but created others. When we introduced magnetic fields into the mix, we realized that black holes are not simple. Furthermore, we've realized that under some conditions that aren't even that rare, black holes are simply prevented from feeding. One of these conditions was discovered through the work of physicist Stephen Hawking, who in the 1970s proposed that black holes evaporate. The mechanism, which became known as Hawking radiation, works through quantum effects at the edge of the black hole, causing them to lose energy. And since energy and mass are equivalent, for a black hole to lose energy, it loses mass. However, in the process of losing mass, the black hole emits Hawking radiation. And it makes the black hole's accretion process very difficult indeed because the radiation pressure pushes the matter falling towards it far away. It is a kind of barrier. Hopkins even found a relationship between the mass of the black hole and the radiation it would need to emit to create this barrier. Smaller black holes would indeed emit radiation more rapidly and with more energetic wavelengths, evaporating faster, while larger black holes emit more slowly, evaporating more slowly. In practice, this means that a supermassive black hole would take much longer than the current age of the universe to evaporate, while small black holes would have evaporated a long time ago. And here, when I say very small, I mean really extremely small. I'm talking about black holes with sizes very close to that of an atom. If you're wondering whether black holes the size of an atom can indeed exist, you're asking the right question, because that was the same question Stephen Hawking himself asked. In reality, Hawking was concerned with another question, but one thing led to another. The question he asked himself was whether the beginning of the universe could have generated black holes. During the early moments of the universe, there were somewhat random density fluctuations, so in some places the density was higher than in others. But right after those first moments, a sudden and extremely rapid inflation made the universe go from the size of a tennis ball to the size of a galaxy. And all this between 10 to the power of minus 36 and 10 to the power of minus 33 seconds. Hawking realized that during this process, some of these regions with higher density could have collapsed and formed what became known as primordial black holes. And here I need to highlight something which might cause confusion. Often primordial black holes are interpreted as very small black holes. But it's not quite like that. Primordial black holes can come in different sizes, including larger ones. But in this video today, we are going to focus on the smaller ones, and the reason will soon become clear. Hawking concluded that very small black holes, even with masses less than 10 to the power of 15 grams, had already evaporated a long time ago. But the larger ones could still be among us today. There's just one problem, however. They have never been observed. And believe me, we are definitely looking for them. They are absolutely extremely important for physics. Primordial black holes are one of the candidates to explain dark matter. They may not be the most likely, but they are potentially the favorites for 3 reasons. First, we do not need new physics to explain them. Second, they formed naturally. And third, it would be possible to observe them at different mass intervals. But where would these black holes be? Why have we never observed one of them? According to estimates made by Hawking himself, it is possible that primordial black holes with masses close to that of an asteroid exist. They haven't evaporated yet. But where are they? How can we prove that they are dark matter or even prove that they are not dark matter? We have several reasons to believe that primordial black holes exist and in large quantities. Observations of very distant galaxies obtained by James Webb can be explained through primordial black holes. James Webb himself indicates that the formation of galaxies was much faster than we expected, and this remains the greatest discovery of James Webb up to the moment this video was recorded. This could be explained through a process involving primordial black holes. Even the recently observed combination of black holes, where the mass of some original black holes could not be explained through the death of stars, could be explained through primordial black holes. My point is, we have very strong evidence, both theoretical and observational, that these black holes indeed exist. It was using this argument that they might exist that Hawking introduced the central idea of this video. What if primordial black holes were swallowed by stars as they formed? Hawking himself answers this question in his paper, stating that, for a star like the Sun, primordial black holes with a mass of 10 to the power of 17 solar masses could be captured when the dust cloud that formed the Sun collapsed. Since he was one of the pioneers of this idea, these stars became known as Hawking stars. It would be possible that, if a primordial black hole were nearby, or within a cloud of gas and dust about to collapse, it would become part of the star that was born. We know that the formation of a star occurs when a cold cloud of gas and dust collapses, and the collapse can be triggered by an external factor, such as shock waves from a nearby supernova. During the formation of the star, the extremely small black hole, the size of an atom, would be pushed to its center. If you think this would be a feast for the black hole, not so much. There are 2 barriers to stop it from consuming all the material of the star. The first is Hawking radiation itself. The radiation pressure becomes a barrier and the accretion slows down as a result. And the second is the radiation from the accretion process. When a black hole feeds, the accretion disk around it shines, meaning it also emits radiation. And this radiation also creates a barrier through radiation pressure. That's why there is a limit to how much a black hole can feed, even when Hawking radiation doesn't matter as much, as in the case of supermassive black holes. And this limit, or in more technical terms such as the accretion rate, is called the Eddington accretion rate. For the primordial black hole, this becomes an obstacle. The mass of the star falls into it slowly. So it would take a long time to grow, something on the order of billions of years, sometimes even longer than the star's own age. Also, the energy and luminosity around the black hole would start to add up with the luminosity of the star. This creates a sphere within it, dominated by the interaction with the black hole. And the more it grows, the more this sphere grows. In the early life of the star, most of its radius is dominated by hydrogen fusion. This is similar to what we observe in the Sun and in many other stars. There would be no difference between seeing a common star or a Hawking star at this stage. But as the primordial black hole feeds and grows inside the star, the sphere of influence, called the Bondi sphere, also grows. And with that, the luminosity the black hole emits when it feeds starts to match and even surpass the luminosity emitted by hydrogen fusion. And this is extremely dangerous for a star. They live in a delicate balance between gravity, making them shrink, and radiation pressure, making them expand. With more luminosity, or rather radiation inside it, the star begins to swell slightly, not enough to become a giant or supergiant. It would become a type of star smaller than a red subgiant. It would stop growing because, as it swells, it becomes difficult for the black hole to feed again. The star's matter no longer falls so easily, so it is pushed back by the high radiation pressure. And with that, the primordial black hole reaches a plateau, as does the luminosity it emits. At this point, the star would live solely on the energy generated by the black hole, because nuclear fusion would have already been halted. What you would see when looking at such a star is exactly what you would expect from a red giant star, except that it would be dozens or hundreds of times smaller than usual. If a Hawking star would look normal throughout its entire life, then how can we possibly find them? One possibility would be to look for red giant stars that are much smaller than expected. But this would not be a guarantee, because there are other natural processes that can also affect the size of stars. So size alone is not a guarantee. But there is a glimmer of hope in an area of astronomy that you have probably never heard of. Astrosismology. It studies the frequency spectrum of stars, and what these difficult words mean is that it basically studies how a star vibrates. A star has a quite complex dynamic in its interior, where the plasma moves along with magnetic fields. And this movement from the interior causes pressure waves to pass through the star. In a simplified way, take a musical instrument. The way you move the strings or how you strike a fabric causes the air to vibrate and a pressure wave to pass through it. This is what we know as sound. You can even easily distinguish between different types of instruments that have played the same note, which is what we call timbre. And if your ear is very well trained, you can even differentiate which specific note is being played by which particular instrument. A star is not much different. Their plasma is a fluid just like air. In the same way that you can determine the characteristics of a musical instrument through its vibration, stars with different characteristics also vibrate in different ways. And this vibration can give us various additional important information about the interior of a star and its different properties. So, by knowing how a normal star vibrates, we can analyze this spectrum and compare it with those we suspect to be Hawking stars, because the waves passing through the black holes would be forced to propagate differently. In the same way that if you put tape on the strings of a guitar, it will sound slightly different. Astrosismology could indeed be the way we find Hawking stars throughout the universe. But what if these stars are not throughout the entire universe? What if they are much closer than we had imagined? Like in our Sun. All the analysis that the articles did, along with the simulations, are of stars similar to the Sun. So everything mentioned in the video also applies to the Sun. The point is, we wouldn't know if the Sun is a Hawking star or not, since visually they would look the same. So for us, it wouldn't make much difference if the Sun had or didn't have a primordial black hole at its center, although it would be really cool to say we orbit a black hole. However, the difference would be at the end of the Sun's life, and that indeed could affect the Earth. At the end of its life, a Hawking star becomes a type of red giant, which the Sun will also become at the end of its life. The difference is, a Hawking star reaches this stage billions of years earlier than a normal star. So in this case, the Sun would die much sooner than expected, and humanity would have a few billion years less. The silver lining of all this is currently we expect at the end of its life the Sun will expand to engulf Earth's orbit. But if it were a Hawking star, it would stop in Mercury's orbit. The view from here on Earth would be incredible, but deadly. So, what's the verdict? Is the Sun a Hawking star or not? The field of astrosismology can only reach a certain depth. So, it is absolutely certain that there is no black hole much larger than an atom inside the Sun. If there is indeed a black hole inside the Sun, it must be an extremely small primordial black hole, beyond the depth we can currently reach. So, to answer, we will indeed need to enter the realm of probability. There is actually a very, very, very low chance that the Sun is an extremely rare Hawking star. First, if the Sun accreted a primordial black hole during its formation, by now it would be large, to the point of appearing in asteroseismology analyses. It is unlikely that a primordial black hole has gone all this time without feeding, considering the difficulties mentioned. Second, the chance of a primordial black hole having entered the cloud in the location that formed the Sun is low. And we can confirm this by looking around. We can see that the red giant stars near us are of normal size. So the odds certainly suggest that the Sun is not indeed a Hawking star. If the existence of Hawking stars is ever confirmed, it would truly be an excellent way to study primordial black holes. We could most likely even determine whether or not they are related to dark matter, which is one of the greatest mysteries of the universe today. But a part of me can't help but find it incredible that, if their existence is confirmed, they've been hiding right under our noses all this time, inside stars. And this would indeed only show that we know significantly less about the universe than we thought. And if you like topics like this, don't forget to definitely subscribe to the channel so I can make more. Thank you very much and see you next time.